All right, so we'll talk about numerical methods, or let me say numerical computation, right, of eigenvalues. So if you remember last week when I spoke about convergence of iterative methods, or last time when I spoke about convergence of iterative methods, we did speak about some things like condition numbers, and then we ended up speaking about spectral radius, and we spoke about the spectral radius being the eigenvalues of the system. So it means that it is really important for us to understand what eigenvalues are and how we can compute eigenvalues. Okay, so usually to determine the eigenvalues, if you have a matrix n by n and you want to determine the eigenvalues, we construct a characteristic polynomial. We construct a characteristic polynomial, which is usually maybe 3 lambda, which is equal to the determinant of your matrix minus lambda of I, where I, right, where I is a unit matrix, and then we determine the zeros, right? We determine the zeros of such a matrix, or such a polynomial, and then these zeros is what we usually call the eigenvalues. Once you determine these zeros, you come to the eigenvalue. You then find the eigenvalues of the problem of the system. And the computation is a bit expensive. Some of the difficulties are that you need to find the determinants. Yeah, so again, in the computation, we know that you need to find the determinants, right? To find determinants. And this is, we've shown that this is usually computationally expensive to find the determinants. We spoke about it from when we started with Cramer's rule, how to compute the solution of a system of linear equations. We spoke about the Cramer's rule, and we said that we need to compute the determinants, and these are really expensive computations. So it's very difficult, really, in that sense, arriving at the eigenvalues when you have large sparse systems, especially. And so for this reason that is important, we at least understand how or what are some of the methods that we can use to circumvent these ideas concerning computing the eigenvalues. But so before that, I'll go briefly over some definitions that I feel are important that you should know. But just briefly, so there is one that we will have if we say that we have some linearly independent vector sets. What does it mean? So if we have K, and we say that it's a set of vectors, we say that the set is linearly independent, right? Linearly independent if whenever 0 is equal to alpha 1 v1, sorry, v1, 1 is up, alpha 1 v1 plus alpha 2 v2 plus alpha k uniquely, then alpha 1, alpha 2, up to alpha case are 0. So if they are linearly dependent, this is what we mean. Otherwise, the set of vectors, okay, is linearly dependent. So I need this definition of linear independence and for you to understand the independence of it. And then what does it mean? What does it mean again? So let's go to next page. Again, if we have such a case, and this is theorem, I'll say theorem 2, if we have these vectors, v1, v2, up to vk, and they are sets of, no, let me make it n. There are a set of n linearly independent, right? All right, it's like this, vectors in Rn, then any vector x in Rn can be written uniquely, right, as x v1, beta 1, v1 plus beta 2, v2 plus beta n, vn. For some constants v1, beta 1, beta 2 up to beta n. Okay. So if you take a linearly independent vector, okay, if you take a linearly independent vector v in Rn, and you take any vector also in Rn, then you can write this vector in Rn uniquely as a combination of this vector and some constants. So basically, we have written I1 and beta I vi of some constants, beta 1 v1 up to beta n vn. And this it is possible to prove. I will not prove it here because this is linear algebra class. And again, you can check if we have v1 to be 1, 0, 0 plus transpose. If we have v2 to be minus 1, 1, 1 transpose. If you have v3 to be 0, 4, 2 transpose. And you have alpha 1, alpha 2, and alpha 3, then we can check linearly independence. It means 0 is equal to alpha 1 v1, alpha 2 v2, alpha 3 v3. Right? And basically that means 0, 0, 0 transpose alpha 1 of v1. Let me write it out. And this will be alpha 1, 1, 0, 0 transpose plus alpha 2 minus 1, 1, 1 transpose plus alpha 3, 0, 4, 2 transpose. So if you solve for this, you realize you will come to alpha 1 minus alpha 2 is equal to 0. Alpha 2 plus 4 alpha 3 is equal to 0. And alpha 2 plus 2 alpha 3 is equal to 0. You have 3 equations in this form. So if it is linearly independent, then we say that there's only solution, right? The only solution we have really is alpha 1, alpha 2, alpha 3 are all 0. And thus, you can say that the sets V1, V2, V3 is linearly independent in R3. And then we say that if it is really linearly independent, then we can take any elements in X3, in R3, where we can say maybe this is X1, X2, X3 in R3, and we can write this as a sum of beta 1 V1, beta 2 V2, beta 3 V3. Okay, and then if you can write this, you realize that you also have to choose your beta 1 to be X1 minus X2 plus 2X3, beta 2 to be 2X3 minus X2, and beta 3 to be half of X2 minus X3. And so this becomes those constants, right, that we spoke about in this theorem, that if in this theorem, right, that if you have a linearly independent vector in Rn, then you can take any vector x, which is also in Rn, and you can represent this uniquely by a summation of the linear vectors, a product of the linear vectors and a constant beta as well. And this, we have demonstrated that we can actually do this. So now your vectors, x, you can now write them in terms of this beta 1, beta 2, beta 3. So it's important we understand this because in the next theorem, which is theorem 3, if we have a matrix A, if A is a matrix, and lambda 1, lambda 2, up to lambda k are distinct eigenvalues of A with associated eigenvectors x1, x2, up to xk, then x1, x2, x3 is linearly independent. So now we can actually use the idea of eigenvalues. So if you have a matrix and you have distinct eigenvalues and you have an associated eigenvector to your eigenvalues, then these eigenvectors are linearly independent. So if you understand linearly independent from here, then you'll be able to match it exactly in this. And this is very, very important for us to understand. And this is why I spent some time to explain the concept of eigenvalues, linearly independent. Okay. So maybe I go briefly in the diversion because I want to talk about orthogonal and orthonormal vectors as well. So if we have a set of vectors, v1, v2, up to vn. If we have a set of vectors and we call this set of vectors orthogonal, if VI transpose VJ is 0 for all I not equal to J. If, in addition to this, VI transpose VJ is 1 for all VI for all I 1, 2, up to N, then the set is orthonormal. So we are talking about matrix, its eigenvalues, and then its associated eigenvectors. And we say that these eigenvectors are linearly independent. If we have a vector, a set of vectors, V1 to Vn, we say that they are orthogonal, right? Orthogonal if the product of any two vectors, okay, any two of these vectors, if their product is 0, such that it is not the vector itself, then we say that it is orthogonal. If, however, the vector in itself, the product of the vector in itself is also giving you 1, then you say that it is orthonormal. So, in passing, we say that if, right, for instance, we know that if we have X and we find the transpose of X, we can write it in terms of normal, in terms of the norm as the true norm. So if we have a set of orthogonal vectors, V1, V2, up to Vn, we say it's orthogonal. Orthogonal is orthonormal if and only if Vi is the true norm of the vector is 1, then we say that it is orthonormal for each I 1, 2, up to N. So, example, if we take V1 to be 0, 4, 2, V2 to be -1 over 5, 2 over 5 transpose. And we take V3 to be 1 over 6, -1 over 6, 1 over 3 transpose. Form an orthogonal set. The L2 norms of these vectors, right? The L2 norms of these vectors are, so basically means take V1, find the L2 norm, and you have this. If you take V2, you have L2 norm as square root of 30 over 5. I'm thinking you already know the definition of these norms. I gave them. And then if you take V3, the L2 norm is 6, square root of 6 over 6. If, okay, again, if we can write U1 to be V1 over the L2 norm over its L2 norm. Then we'll have 0, 2 square roots of 5 over 5, square roots of 5 over 5 transpose, and so on up to U3. U3 will be V3 over its norm, 2 norm, and this will be square root of 6 over 6 minus square root of 6 over 6, and then 6 over 3 transpose. And we'll say that if you find U1, you'll see that the true norm of U1 is 1. Is equal to the true norm of U2, and is equal to the true norm of U3, and they are equal to 1. This is important because in theorem 5, we say that an orthogonal set of non-zero vectors is linearly independent. So, critical information: if you have an orthogonal set of non-zero vectors, then you know that it is linearly independent.
Please, can I ask question?
Yes, go ahead, ask.
My question is this orthogonal and then autonormal vectors. So come into the real life scenario. So where can you apply, or what does it actually mean in the real life? Fine, we know how to compute, but in real life.
Yeah, so you know, we all this thing is we are trying to compute the eigenvalues. We want to compute eigenvalues. We want to understand what are the ways by which the matrix A here, okay, connects to the eigenvalues. Then what we started by saying was that if you know the matrix A and you know the eigenvalues, the eigenvectors of the matrix associated to the eigenvalues are all linearly independent. So we are trying to understand these concepts because we are going to use them. Because that's if I start talking about the matrix decomposition, which I'm going to talk about next, you see that I'm using these concepts again. But so it's important you understand, because this is linear algebra. But now we are going to apply them in decomposing sparse matrices. And we want to find a connection, how this is going to connect to the solutions of this decomposition. If you do it, does it really relate to the matrix itself? Right? So we are saying that if you have eigenvalues of the matrix, the associated eigenvectors are all linearly independent. Then we say that if you have a set of vectors, we say that in the set of vectors, if these vectors multiply themselves and they give you 0, we have, if they are not the same, then they are orthogonal. If the vectors multiply and then they give you 1, then they are orthonormal in addition to your orthogonality. So we are not done. We need to try to understand orthonormal, orthogonal, and then now I'm saying that if you have an orthogonal set, of non-zero vectors, we are also linearly independent. So we have connected first the eigenvectors to linearly independence. We have connected we said if you are linearly independent, then we can create a unique vector as well. So we have connected this one as well. So we are trying to see linear independence. How does it connect to a system, and this is what we are heading to. So first, now we know that the linear independence also has something to do with the eigenvectors. Then we define orthogonal set because this is also a set of vectors. If these set of vectors have a special characteristic, because you know you have eigenvectors here. These eigenvectors are also a set of vectors. So they can be orthogonal vectors. What does it mean? They can be autonomous vectors. What does it mean? So this is where we are building onto. So we define orthogonal and we define orthonormal. I give example of what it means by orthonormal and orthogonal, and then I say that truly an orthogonal set of non-zero vectors is linearly dependent. But if you go back here in theorem 3, you see that I say the eigenvectors of the matrix associated to the eigenvalue with the state eigenvalues are linearly independent. But now I'm saying that an orthogonal set of non-zero vectors is linearly independent, right? So if you have eigenvectors which are orthogonal, then you know that they are linearly independent. And you can build up again from there. But let's go on because the next one is really going to help us proceed further. In a way, if I define, let me define, if I have a matrix Q is said to be, so this week I'm going to give you a lot of exercises that you submit on Friday. To be orthogonal matrix if Q inverse is equal to Q transpose. So if you have an orthogonal matrix Q, which is formed from an orthonormal set of vectors, then you know that Q inverse is equal to Q transpose. This basically means that Q transpose of Q should give you the identity matrix. This is what we mean. So if you have an orthogonal matrix, then the transpose is equal to its inverse. So you don't need to go and try to compute the inverse. You can just find it. You can just use the transpose, and that's fine. Okay, so I will try then to talk about some two other definitions, and then we can proceed with the most critical method for the eigenvalues, which is the power method. But before that, I want to talk about some other definition that I think we should know. What we mean by two matrices A and B are said to be similar if a non-singular matrix S exists with A equal to S inverse B of S. Similar matrices have the same eigenvalue. And this, in the next theorem, is that I'll give as an exercise is that if you suppose A and B are similar matrices with A equal to S inverse, with A equal to S inverse BS, and lambda is an eigenvalue of A, with associated eigenvectors X, then lambda is an eigenvalue of B with associated eigenvector S of X. So this is an exercise. So it means that you must first think of eigenvectors, eigenvalues of A, and then use the idea of similarity, right? Similar matrices. Then you'll be able to show that truly, if you have similar matrices A and B, then, and if you have an eigenvalue of A and an associated eigenvector X, then the same the lambda is as well as eigenvector of B and is associated with eigenvector S of X. So this will be an exercise. I'm giving you the definitions that you need and then what you need to prove. I mean, it's like 4 or 5 lines. It's not a difficult exercise. It's just to test if you understand connections between eigenvalues, eigenvectors, and similar matrices. Then finally, one of the things I also want to talk about here, maybe the last 2 things I'll talk about here. One, be assured that if you have a matrix A, okay, if you have a matrix A, like an arbitrary matrix A, and you have a non-singular matrix U exists with the property that C is equal to U inverse A, where T is an upper triangular matrix whose diagonal entries consists of the eigenvalues of A. So if you have a matrix, then you can also have non-singular matrix that exists such that this property holds, and that you can write your matrix and then as an upper triangular matrix whose diagonal entries are the eigenvalues of it. Okay. So maybe to end this part before I start the power method, what I'll say is that if you have a symmetric matrix as well, A is positive definite. We spoke about positive definite. If and only if all eigenvalues, right, of A are positive. So you see that with eigenvalues, you can still try to, because we know the different matrices, we can still try to tell the connection of these matrices and their eigenvalues. So we say, for example, if you have a symmetric positive definite matrix A, or you have a symmetric matrix A is positive if and only if all its eigenvalues are positive. This is also very easy to prove. And then one important thing about eigenvalues is this theorem called the Gauss-Green theorem. Gauss-Green theorem. Really, really important. We say that if you have an n by n matrix.
Sorry, sir.
Yeah.
Please, what's the pronunciation of that? You say it's what?
Gauss-Green circle. Gauss-Green circle. It says if you have a matrix, A and you have an Ri, which denotes the circle in the complex plane, with center AII and radius the sum J not equal to I to n and J from 1 of Aij, that is R I will be equal to Z C such that Z minus AII is less or equal to N J1 J not equal to I J. So the eigenvalues of A are contained in this site, are contained within R, which is a union of all these circles, I to N. And moreover, the union, let me put it that way. The union of these circles do not intersect. The remaining n minus k contains K So let me give an example. If you take A 411 021 minus 209, and the Gaussian cycle just says that if you take this one, take this one, take this one. If you take R1, then it says Z is in C, and Z minus 4 diagonal is less or equal to the sum of diagonal, right? So this is 1 plus 1, which is 2. Take R2, Z is in C, and Z minus 2 is less or equal to 0 plus 1. Just take R3, Z is in C, and Z minus 9 is less or equal to minus 2. So sorry, the absolute values, right? It's the absolute values. So that you don't get confused. The absolute value 1 plus absolute value of 1 plus absolute value of 0 minus 2 plus absolute value of 0. So cells R1 and R2 are those joints. I'll draw it for you to see what I'm meaning. It's joined from R3 there are only 2 eigenvalues. Within R1 union R2 and 1 within R3. So the spectral radius of A is the maximum I maximum of all the eigenvalues. We have 7 is less than the spectral radius of A less than 11. So if we plot, don't forget we said we had a complex plane, so this is the real, this is the imaginary. In the first instance, we said Z minus 4, Z minus 2, and then Z minus 9. Z minus 4, we said, is less than or equal to 2. Z minus 2 is less than or equal to 1. And Z minus 9 is less than or equal to, also is less than or equal to 2. So if we put some numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4, something like that. Then Z minus 4, if we take 4, if this is 4, Z minus 4 less or equal to 2 means that we have a circle of radius 2. So go up to here, come all the way here. Then we have Z minus 2 less or equal to 1. So if we go to 2, then we have radius 1. So we go here all the way. Then if we take 9, 4, 5, 6, 7, 8, 9, 9. 9 also was what? We had z minus 9, that's what equal to 2. So well, 9 will be here, 9 will be here. Right? So 4, 2, and 9. And then we go off. So what we say by guess scoring is that you use it to determine, you can use it to determine where the eigenvalues lie. Okay, where the eigenvalues are lying. So for instance, in this 2 case, we know that there are 2 eigenvalues here. And then here there is 1 eigenvalue. So Gaussian circles is a way of getting an idea of where your eigenvalues are lying or where they are situated. Okay, so they kind of they provide, sorry, so I guess Gaussian circles provides, so let me write the scoring. Circles. It provides the bounds for the approximation of eigenvalues. So it gives you the bound within which the eigenvalues will be lying. And that's really, really important because sometimes you don't need all the eigenvalues. So just an idea of where they are located is enough. All right, so next, I'll start by talking about first method. Okay. I may not go to the second method, which is also equally important, but just the first method. And I'll give you some work to do, which is the power method. So the power method is an iterative method. We have learned iterative methods. An iterative method to determine the dominant eigenvalue of a matrix. Of course, by slight modification, it's possible to also determine the other eigenvalues as well. Note, it also produces the associated eigenvectors. So how do we compute the power method? It's really very simple. To start, we assume that the matrix A, which is n by n, has n eigenvalues. Lambda 1 up to lambda n, with associated collection of linearly independent eigenvectors, V1, Vn. Moreover, we assume that A has precisely one eigenvalue, lambda 1, that is the largest in magnitude. So that the absolute value of lambda 1 is greater than the absolute value lambda 2, which is less or is greater or equal to the absolute value of lambda 3, and so on. So now, if x is any vector in Rn, then since our vectors v1 to vn is linearly independent, it implies there are constants beta 1, beta 2, up to beta n, such that x can be written as j1 to n of this beta j and bj. You see where we are now. We want to compute the eigenvalues, but where do we start from? We start from our matrix A n by n has n eigenvalues lambda 1 to lambda n, and associated eigenvectors, right? Eigenvectors which are linearly independent. If we say that the eigenvectors are linearly independent, then it means that we can have a unique representation of these eigenvectors. And this unique representation, what we say that we can write them as x equal to j1 to beta j bj. And this is what exactly I wrote here earlier on, that here, you see this theorem. It said if you have a set of linearly independent vectors in Rn, then any vector in Rn can be written uniquely using your linearly independent vectors and some constants. So this is the application. So now you can write your x to be a sum of the products of some constants and your linear and your vectors. So what do? You have x on the left. You can multiply your x by an a, right? So multiplying, let me change my color again. If you multiply both sides let me call this I. Both sides I by a squared up to ak. Then you have ax is equal to summation j1 to n bj avj. And this is nothing but j1 n j1 to n beta j lambda j bj. If you do a2 of x, then summation j1 beta 1 lambda j a bj. And this will be summation n j1 to n beta j lambda square j bj. Dot, dot, dot. ak of x and j1 beta j lambda j k bj. So you can write any multiple of a, right? Any factor of a in terms of the eigenvalues and the eigenvector and the constant beta. So if your eigenvalue 1k is factored out, it's factored from each term on the right side. So let me call this one the right side of I, then ak of x is equal to lambda k summation j1 beta j lambda j lambda 1 k of bj. Since lambda 1 is greater than lambda j for all j to 3 up to n, we have the limits k going to infinity of lambda j over lambda 1 to the power k is 0. And the limits k going to infinity of ak of x will be the limits k going to infinity lambda 1k beta 1k of b1. The sequence converges to 0 if lambda 1 is less than 1 and diverges if lambda 1 that is greater. Greater than 1. Provided, of course, that beta 1 is not equal to that. Let me call this equation A. It can scale, right? So this equation, we can scale it. By scaling the powers of AKX in an appropriate manner, to ensure that the limits in equation A is finite and non-zero. Sorry. We can ensure the limit in A is finite and non-zero. How do you scale? How do you scale? The scaling begins by choosing an appropriate X. To be the unit vector X of 0. Relative to this infinity norm and choosing a component using a component x0 x0 b0 x with x0 p0 to be equal to 1 and the infinity norm also equal to 1. If you take y1 to be ax0 and you define mu1 to be y1 p0, then because p0 is power method, then mu1 is equal to y1 p0, which is y1 p0 over x0 p0, which is equal to beta 1 lambda 1 mu1 p0 plus sum J2 beta J lambda J P0 J beta 1 V1 P0 plus sum J2 beta V2 J, which is equal to lambda 1 beta 1 V1 V0 plus J from 2 beta J lambda J over lambda 1 Vp0 of J all over beta 1 V P1 plus NJ2 beta J Vp0 of J. If you take another P to be the least integer, such that y1 P1 is equal to the norm 1, infinity norm 1 of y1, and you define x1 by x1 to be 1 over P1 times y1, which is nothing but 1 over y1 P1 times ax value. Then x1 P1 is equal to 1, which is equal to x1. Now we define y2 as ax1, which will be nothing else but P1 A2 x. And you can define mu3 to be yp1 which is y2 p1 over xp1, which will be beta 1 lambda 1 ap1 of 1 plus sum j2 beta 2 lambda squared ap1 j all over beta 1 lambda j2 beta j lambda j j1 over yp1, and this will be lambda 1 beta 1 plus sum j2 beta j lambda 1 to P1 of j. beta 1 j p1 j2 beta j lambda j lambda 1 bp1 j. Then we do P2 to be the smallest integer. Yp2 of 2 will be y2 with infinity. So we have computed x1, we have computed y1, x1, and then now y2. And with that, we can also compute x2. And then we generalize. Then define x2 to be 1 over y2 p2 times y2 p ax plus 1 p2 y3 times a squared x7. So similarly, we can define the sequence xm m0 to infinity ym m1 m1 to infinity, and a sequence of scalars, right? Scalars mu m from 1 to infinity inductively by ym is equal to a x m minus 1, and then mu m is ym bm minus 1 is lambda 1 beta 1 v1 p m minus 1 plus sum m j2 lambda j lambda 1 m beta j v m minus 1 j. And beta 1 v1 p m minus 1 plus sum m j2 lambda 1 m minus 1 beta j v j p m minus 1. And this will give us x m, which is y of m, I v m, and this will be nothing but a m x product k1 y pk of a. And we are sure that each step where at each step Pm is used to represent the smallest integer for which y is equal to the non-infinity norm let me call this equation here. And then we realize that from equation B, lambda J over lambda 1 is less than for each J, 2, 3, and so on. And the limits I'm going to infinity mu n is equal to lambda. Provided that x0 is chosen so that beta 1 is inside. And this is what we call the power method. Disadvantage is that, because after that I'll do one example for you to see. Disadvantage is that one, it is known let me write it this way. It is unknown at the outset whether or not the matrix has a single dominant eigenvalue. No, make it true. It is known how x0 will be chosen so as to ensure that its representation in terms of eigenvectors of the matrix will contain a non-zero contribution from the eigenvectors. Okay, so let's take an example for you to see how this is done. Example, if you have A minus 4, 14, 0, minus 5, 13, 0, minus 0, minus 1, 0, 2, And we know that the eigenvalues of this is 6. Lambda 2 is 3. Lambda 3 is 2. Then by power method, if we start x11, x0 should be 111 transpose. Then compute y1 8 and 0 to be 10, 8, 1 transpose as well. So that y1 infinity is 10. And mu1 is y1, which is also 10. And x1 will be y1 to be 1, 0.8, 0.1. So you start with x00, x0 given by 111, then you compute y1. Then you find the infinity norm of y1. Then you the scalar, you find the scalar mu1. This scalar is nothing else but y1, the first term in the y1, right? So it's 10. Then you use this to compute your x1. So x1 now is just your y1 over this scalar that you have chosen. So you can do the same for y2, right? And now you go to, you have x1, so you can go to y2. And then for y2, you know it's nothing but 8 squared x0. And then you also find the infinity norm of y2. You find a scalar, and then you find x2. Right? So another step, which then you can continue, is find y2. Is find y2, which is nothing but ax1. You can take it like that, right? You know your x1, so you can multiply by your a, and then if you do that, you get your y2. Then you find your infinity norm of y2. Then you choose your scalar omega 2, which is then you can do your x2 to be y2 over y2 p2. So that's how the power method works. Very, very easy and straightforward. If you continue like that, you will generate for every m 0 up to some number n. You can create an xn. It's a vector, right? vector. So if we started from 1, 1, 1, we can continue. Yeah, for instance, when I did it at 12, so maybe I stopped at 12, and at 12 I got 1 0.7143, 1 0.2 4989. Then you have some mean of m, and at 12 I got this to be 6.000837 and so on. And this gives us, if we go back, we have the eigenvector here, and then this here gives us the eigenvalue, and this corresponding eigenvector. Okay, of course, there are certain things that you can ask yourself. One is if A, see in this case we choose an arbitrary matrix. A is symmetric. We have what we call the symmetric power method. So if A is symmetric, it's faster, we can arrive at eigenvalues, again, but dominant eigenvalue faster than when it is not symmetric, for instance. Then there is a method 2, which is called the inverse power method. So the inverse power method, similar to the power method, right? So it's just a modification. It's a modification of the power method. That gives faster convergence. So in this case, it is usually used, to determine the eigenvalue of A closest to a specific number Q. So if you have A, which has a certain number of eigenvalues, and then you choose a certain constant Q, you can use the inverse eigen method to find this eigenvalue, to determine this eigenvalue as well. So I will not tackle this as well, so that I can go on to some other stuff that I want to do. So I'll give you a very important one as well, which is the householder method. Right? This is a very popular one. So here we use the QR method, right, to reduce asymmetric tridiagonal matrix. A similar matrix. Similar. Don't forget what we said about similarity. That is nearly diagonal. The diagonal entries and the diagonal entries, in this case, of the reduced matrix, yeah.
I want to know something. I want to know the importance to find the dominant eigenvalue or eigenvalue.
I mean, it's like, yeah, what you're asking me is, why do we need eigenvalues, basically, right?
Yeah, the dominant eigenvalue or eigenvalue.
I mean, so we spoke about the spectral radius of a matrix.
Okay.
And the spectral radius, when we spoke about it, we said the spectral radius is actually what we need in the spectral radius definition is the dominant eigenvalue.
Okay.
So if you know the dominant eigenvalue of your matrix, it can tell you if your matrix is ill-conditioned. It tells you, it gives you a lot of ideas of what the matrix is, the behavior of the matrix.
Okay.
So usually, I mean, we can do this analytically, but in computational sense, for instance, if you want to do if you want to find if you are doing diseases, epidemiological models, for instance, when we are doing epidemiological models, when we want to find the endemic equilibrium, the disease-free equilibriums, and all these things, we use the idea of the Jacobian. Then we use it to find the eigenvalues, and we use a spectral radius to find the dominant eigenvalue, which we then use to talk about whether the disease is endemic or is disease-free and all these things. These are the things we discuss when we're talking about when we are doing epidemiological models. So eigenvalues tell us a lot about the system, tells us a lot about a matrix. And then the matrix, it can be coming from a system of equations, example being an endemic epidemiological models. It can also be from ecological models. It tells us a lot about ecological models, the behavior of these models. So that is why we need these. The idea of the spectral radius or the eigenvalues are very critical, and we try to discuss them. But not only that, even for things like PD, when you discretize your metrics and then you come to a system of linear equations, AX is equal to B, you can tell a lot. If you know a lot about your metrics, whether it is ill-conditioned or not, you can find a better way of solving your system. If it is ill-conditioned system, then you know what maybe you can do some other techniques to solve it. So determining the eigenvalues immediately tells you a lot about your system as well. So that's why it's really important we understand the whole idea of the eigenvalues.
Yeah.
Okay, so I'll just a brief explanation. I've spoken about inverse power method. Of course, I didn't describe how it looks like, but once you know how the power method looks like, it is very straightforward to really see how the inverse power looks like. Inverse power method looks like as well. Another method which is a bit also different, but of course falls also in line with when we spoke about orthonormal matrix vectors, because we use QR. QR is another matrix decomposition method, which is just composing your method, your matrix A into orthogonal vectors. Is that if you use this householder method, you can take a QR method and then apply it to a symmetric diagonal matrix, right? And reduce this to an almost diagonal matrix. So this is what this householder method actually looks like. Of course, I'm not going to talk about it, but just probably will give you an insight how to prove it. It's not that complicated, honestly. Not that complicated.
Okay.
All right. So finally, I'll spend the last 1 hour and then talk about numerical. Numerical computation. So sometimes what happens, so I mean, any question, let me just, for the sake of officiality, let me ask any question.
No, I don't think.
So, final part, numerical. Okay. Numerical integration. Okay, so if you have, so here, let's talk about methods for approximating definite integrals. Of the form where f is continuous with a finite interval AB. And these methods are called numerical quadrature. coverage. Why do we need these? Why do we need these? Why numerical integration? The integrand f of x may be known only at certain points. Two. The formula for the integrand may be known but may be difficult or impossible to find an antiderivative the same as an integrand. Example, f of x is equal to e s squared over 2 square root of pi to 1. Sometimes it may also be possible to find an antiderivative symbolically. But may be easier to compute a numerical approximation. First method called Newton Cotes integration. Let f be a function whose values are known at evenly spaced points x0, x to x. That is sk minus 1 should be h k from 1 to up to n. Evenly spaced. So it means that if we have a line like that, we're going to create an even space such that we have this sk minus 1, sk plus 1, where the difference between where the difference between SK and SK minus H evenly spaced. So evenly spaced, a minute. I think I missed something that we need to talk about. I missed something I need to talk about, so I'll go back. I'll go back. Before needs the course. Yes, we need to address this before. I mean, it may be just a revision, but I think it's still important. Sorry. So usually we have polynomial interpolation methods, right? I'm not sure if you have treated such a thing before. We have polynomial interpolation methods that we usually use to solve problems. So if you have from the other slide, if you have let me go. So we note that the method of quadrature methods are based on interpolation polynomials. So example, we have a branch polynomials. We have Newton's polynomials. We have cubic polynomials. We have B-splines, and so on. Okay. And how do these polynomial methods work? We select a set of distinct nodes x0 to xn from the interval AB. This is the interval of integration, right? Then we integrate. The interpolating polynomial. Interpolating polynomial. Example Lagrange as follows. Pn of x, the sum I from 0 to n f of xi and I x, where Li are Lagrange polynomials. And we have some truncation error. Truncation error 10 over AB to obtain integral a to b x to x is equal to integral AB sum n 1 Li of x dx plus AB add 0 to n x minus xi f n plus 1 x over n plus 1 factorial dx. And this will be sum ai f xi plus 1 over n plus 1 factorial a to b 1 to n xi x 1 x where star x is negative each x ai is ab and I x for each I 0 1 to n. Quadrature form. Yes. Integral of AB f x is approximately I, the sum of x with an error given by error function f 1 over n plus 1 factorial AB product of n I from 0 x minus xi f n plus 1 x. So in case, let me just consider, for instance, if we use Lagrange polynomial. I'm thinking you know what the Lagrange polynomial is, but let me try to look for it and write it out for you. Okay, so we have Lagrange polynomial. Example, if you are using the Lagrange polynomial, then example, if you are given x0, x1, and y0, y1. To determine a polynomial that passes through this point. That passes through these points. It is the same. Approximating a function f for which f of x0 is y0 and f of x1 is y1. We define L0 to be x minus x1, L0 minus x1, and L1 to be x minus x0, x0 minus x1, and then define the polynomial p of x to be L0 of x, f of x0, L1 of x, f of x. Note that L0 of x0 is 1, L0 of x1 is 0, L1 of x0 is 0, and L1 of x1 is 0. So we have P x0 equal to 1 times x0 and 0 times fx. This fx0 y0. And px1 is 0 times fx1 plus 1 times fx1. Fx1 is 1. So forth and so on. So with that, one is able to write a Lagrange interpolation function with this idea, right? With this idea, you can write that if x0, x1 up to xn are n plus 1 distinct numbers, and f is a function whose values are given at these numbers, then a unique polynomial p of x of degree at most n exists with f x k v x k for each k 0, 1, 2 up to n. And this polynomial is given by dx is f field of l2 x plus fxn ln of x, which is equal to k0 fxk ln k x, where for each k 0, 1 up to ln k of x is x minus x0, x minus x1, x minus xn, all over xk minus x0, sk minus x1, up to sk minus x, which is the same as x minus xi over sk minus xi, I from 0 to n, I multiplied. Sometimes it's lk of x to be the same as lk. So if you know that, and now good. So that brings us to the Lagrange. So it means you can write the polynomial function in this way. So I've tried to explain the Lagrange. Next, I want to talk about using this Lagrange polynomials, first and second degree, gives us some types of quadrature, numerical quadrature. Okay, so this numerical quadrature from this Lagrange first and second degree are what we call the trapezoidal and the Simpson's rule. Okay, so let me say that the first and second degree Lagrange polynomials with equally spaced nodes gives the trapezoidal and Simpson's rule. Trapezoidal rule and Simpson's rule. So the next we derive trapezoidal rule. to approximate AB f of x, let x not be A, x1 be B, H be B minus A, and use linear Lagrange polynomial U1 of x minus x1 over x0 minus x1 f of x0 plus x minus x0 x0 minus x1 f of x1. Then integral of AB f x to x is equal to x0 x1 x minus x1 x0 minus x1 f of x0 x minus x0 x0 minus x1 f of x1 dx plus half x0 to x1 f prime prime sum x minus x0 x minus x1 dx. Since x minus x0 x minus x1 does not change. Does not change sign in the interval x0, x1. The weighted mean or the mean value theorem, which is a very popular theorem and be applied. To the error terms, to give x0, x1 star of x minus x1 x prime minus x0 x1 x minus x0 x minus x1 x f prime of sigma x3 over 3 x1 plus x0 or 2x squared x0 x1 of x x0 to x1 is h3 over 6 f prime prime of sigma. So consequently, AB f of x will be nothing but x minus x1 squared over x0 minus x1 3 times of x of x0 plus x minus x0 x0 minus x1 2 times of x1 so squared x1 to x0 minus h cubed over 12 f prime prime of sum. And this will be x1 minus x0 over 2 f x0 plus f x1 and it's h3 over 2 f prime. Since h is equal to x1 minus x0, we have the following. X0 plus x. This is called trapezoid. Because when f is a function with positive values, integral f of x dx is approximated by the area in the trapezoid. So trapezoidal rule simply because we're considering linear function. So if we have A to be x0, B to be xn or x1, and you have a function then limit not be equals. Like that we can draw where we have this and this point, and we can draw a straight line like that. And maybe I should change this step in this step. So if it is this is a first order polynomial, a first degree polynomial that we are using to approximate a function. It's not just any polynomial, but Lagrangian polynomial. So if it is a first degree polynomial, then the error terms are all going to be from the second order, from the second degree. All the error terms will be involving will be in the second or the second degree terms. And you can see that we try to approximate the function by drawing points that connect the end point to the beginning point, drawing a straight line between them. And then this makes it look like a trapezoid. That's where this whole thing about the trapezoid. So we are trying to approximate the blue function. So let me call the f, and then using this p1 to approximate such a function, right? So we say that it gives exact results, right? Exact results when applied to any function whose second derivative is identically zero. And the next rule is Simpson's rule. Now, in the Simpson's rule, we use a second degree polynomials of the Lagrange. Right? So now, this is B Simpson's rule. And this results from integrating over AB second removes x0 to the A, x2 to the B, x1 to the A plus h, where h is B minus A over 2. Therefore, the integral AB f of x dx x0 x2 x minus 1 x minus x3 x0 minus x1 x0 minus x2 f of x0 plus x minus x0 x minus x2 x1 minus x0 x1 minus x2 f of x1 plus x minus x0 x minus x1 x2 minus x0 x2 minus x1 f of x2 x plus x0 to x2 x minus x0 x minus x1 x minus x2 plus 6 f of 3 sine x x. So now you use a second degree polynomial. It means that now you create another point in between your x0 and your x2, right? So Simpson's rule provides the order of 4 error. Error 10. Involving third order derivative. However, it is also possible to derive higher order terms revolving like F4. Do so suppose F is expanded in the third Taylor polynomial about X1. Then for each X, X0 to X2, a number psi with X0, X2 exists such that f of x Taylor approximation f x1 f prime x1 x minus x1 f prime prime x1 over 2 x minus x1 squared f3 f prime x1 over 2. This is f prime prime over 6. Then this is f3 prime 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 x1 over 24 x minus x1 6. This is squared. This is cube. This is 4 x0 to x2 plus 1 over 24 x0 x2 f4 x minus x1 2. Since x minus x1 is greater than 0, equal to 0, and x0, x2, 1 over 24, x0 to x2, f4, sine of x minus x1 to the power 4 to the x is equal to f4, sine 1 over 24, x0 of x2, x minus x1 to x equal to f4 sine of 1 120 x minus x1 to the power 5 x0 to x2. Let me write it down. Equal to F4 1 over 120 x0 x2. What's another sign? X0 x2. However, H is equal to, it is equidistant, so x2 minus x1 squared, x0 minus x1 squared is equal to x2 minus x1 4, x0 minus x1 4 is 0. Whereas x2 minus x1 cubed, x0 minus x1 cubed equal to 2h cubed. And x2 minus x1 to the power 5 minus x0 minus x1 to the power 5 2h to the power 5. Consequently, we are coming gradually. And I'll give you an example more. Consequently, x0 to x2, f of x dx is 2h f of x1 plus h3 of 3 f to the power 3 plus f4 of 60 psi 1 h5. If we place f1 on x1, we place f1 on f1, find the integral x0 to x2 f of x dx equal to 2h f of x1 plus h3 minus 2 f of x1 plus f of x2 minus h2 for f4 sine 2 plus f4 of 60 sine 1 of h5. And this is equal to h of 3 f of x0 is 4f x1 is f of x2 minus h5 4 check F4, phi 2, that's 1 over 5, F4, phi 1. Simpson's rule. If we have x0 to x2, function f of x to x, we say that doing this equally f x0 plus 4 f of x1 plus x2 minus h5 of 90 f4 of psi. And then you know that since the error term involves fourth order derivative, right? F. Simpson's rule gives exact results when applied to any polynomial. Of degree 3. So means that you can approximate function using an integral functions. So example, if you have x squared, okay, we have f of x is equal to x squared on the interval 0 to 2. And so 0 to 2, f of x to x is 0 to 2 s squared dx, right? We can do this exact, but if we use, for instance, Simpson's rule, then Simpson's rule says that, okay, so let's say Simpson, let's use exact. So 1, exact. So exact means 0 to 2 x squared x is equal to s cubed over 3, 0 to 2, and this is 8 over 3, 2.667. If we use, for instance, Simpson, then it says that s squared dx, we can approximate this as 1 over 3 f of 0 plus 4 f of 1 plus f of 2. Right? Where let me replace this by f of x. Right? So now your function, all we're saying is take 1 over 3, 0, put 0 for your function f of x, and now this will be 0. Now put 1 for the f of x, to be 1, and now put 2, it will be what? It will also be 4. And this will be 8 over 3, which is exactly 2.667. But if we use trapezoid, trapezoidal. Then 0, f of x dx. He says trapezoidal says approximate the function by what? What did we write? One over 2 f of 0 plus f of 1. Of 2, sorry, of 2. If you do that, then you have half. F of 0 is 0, f of 2 is 4. F of 2 is 4, and you have what? You have 2. So you see that there is a difference, and this one here gets exact value as compared to the exact. And you can do this for several other functions, and you see that in almost all your functions, the Simpsons get closer to the exact solution compared to the trapezoidal rule. So finally, some few things that maybe I talk about. Some few things that I talk about is definition, because you see that in this example, you see that trapezoidal gives us 2, Simpsons give us 2.667. The exact solution is 2.667. So we want to talk about the degree of accuracy, right? Degree of accuracy. The degree of accuracy or precision of a quadrature formula. Is the largest positive integer n such that the formula is exact for x to the power k for each k 0, 1 up to n. The trapezoidal and Simpsons rule are examples of a class of methods called Newton-Cotes formulas. There are 2 types. Of Newton-Cotes. Formulas. One is open and 2 is closed. One, the n plus 1 points closed Newton-Cotes. formula uses nodes x1, xi to x0 plus ih for I 0, 1 up to n, where x0 is a, xn is b, and h is b minus a over n. It is called closed because the endpoints of closed interval AB are included as nodes. The formula assumes a form integral AB f of x dx n 0 a x I, where AI is x0 x n, and I of x dx is x0 x n, j from 0 j not equal to n, dx. So the error for Newton codes closed forms is that if you suppose that n AIFXI denotes n plus 1 points, closed Newton codes formula. With x not equal to a, xn is equal to b, and h is b minus a over n. There exists psi in AB for which AB f of x to x is equal to sum 0 a f of x I plus h n plus 3 f n plus 2 of psi over n plus 2. So we have 0 to n t squared t minus 1 t times n dt for evenly spaced. If n is even and f is n plus 2 continuously differentiable, and the integral AB f of x dx is given by AIFXI plus HN plus 2 Fn plus 1 of psi over n plus 1 factorial integral 0 to n t minus 1 t minus n dt. And if n is odd and f is n plus 1, continuously differentiable. So many types. So it means that you can write some common, right? Let me finish by this closed Newton codes formula. If n is 1, we said we have trapezoidal. And we said A x0, x1, f of x dx. We can approximate by f of x0 plus f of x1 minus h3 over 12 f by prime of psi. If n is 2, then you have Simpsons, right? Simpsons. And we said we have x0 to x2, f of x dx. This you can do h over 3, f of x0 plus 4, f of x1 plus f of x2 minus h5 over 90 f4 of psi. But because of how we have generated these things, if we take n to be 3, we can also write for even such types where we have f x0 plus 3f x1 plus 3f x2 plus f x3 minus 3h to the power 5 over 80 f4 of psi. And this we call the Simpson's 3/8 rule. Of course, we can do for many types even in between. And we can also talk about the error, the accuracy of these methods as well. And there are several other types of numerical integrations as well. So you can see here we are talking about some very basic or simple ones. The questions will be, what if it's a different type of integration, maybe an exponential function or a sine function? Do we use the same method or we can use a different method? So we have what we call composite numerical integration. The composite. So the Newton codes, I will not go deep into the composites, but just to give you an idea, the Newton codes are unsuitable. they are not always suitable. They are unsuitable for large integration intervals. Also, they are based on polynomials, interpolatory polynomials. Okay, that use equally spaced nodes. So if we are doing certain type of integration where it is not equally spaced, they also will not work. So maybe if I number them, this is 1, this is 2, and this yields inaccurate approximation because of oscillations, the oscillatory nature, high degree polynomials. So in that sense, it is possible to use, right? It's possible to use piecewise, right? We can use piecewise approach to numerical integration. So piecewise approach means for these Newton codes methods, you see, if you have a polynomial like that, you try to approximate it, AB. If we do some sense, we add another one here. So they usually fail if you have really large intervals. We also assume here, right, this is Newton codes, we assume equal spacing. Equal spacing. So if you have non-equal, I mean, if you want to approximate something like that, you have a problem because the oscillations, your polynomial degrees may not be matching. So we try to do piecewise. Piecewise means take them one by one. Take every 2 interval and do it. So that's what this piecewise approach is. You might use piecewise approach to numerical integration. And so with that, if you want to apply the piecewise technique, then it's possible to do even for things like exponential functions and so on and so forth. Okay. All right. So I think with that, I'll stop here. Then I'll share with you some other information that you need for the future as well. So thank you very much. Any questions so far?
No, from this side, no.
Okay. So, yeah, I'm listening.
Yes, doctor. I was inquiring about when you'll be sharing the note that you're organizing.
So, let me stop recording.